I'll invite up, I'll get the bio. Dr. Luiz Brito from Purdue University. We welcome to the front. His topic is opportunities to genetically select pigs for improved resilience and robustness. As we discussed it, we realized that we needed to discuss genetics as well because it often comes up. And Dr. Brito is Associate Professor of Quantitative Genetics and Genomics in the Department of Animal Science at Purdue University, and Purdue's had a long history of addressing some of the environmental insults and the like. Dr. Brito gained his doctoral and postdoctoral training at the Center for Genetic Improvement of Livestock at my alma mater as well, University of Guelph. So thank you very much for joining us.
Thanks so much for the introduction, and good afternoon, everyone. So I would like to start thanking the organizers for the invitation to come here and speak at this conference. It is my first time attending this conference here, and I have really enjoyed it so far. I also want to thank my co-authors, Dr. Jay Johnson from the USDA ARS, and also Dr. Alan Schinkel from Purdue as well. And Dr. Alan Schinkel, he has been a very nice mentor for me over the past 5 years since I joined Purdue, so I'm very thankful for that. So we have been talking in this conference quite a bit about sustainability and what can we do to increase the sustainability of pig production. And I like usually go to the roots and look at the definition. So in the 1987, the United Nations defined sustainability as our ability to meet our needs as well as keep the resources to enable future generations to also maintain their needs. So usually sustainability needs to be defined based on 3 pillars: the economic, the social, and the environmental. And I think the National Pork Board has done a quite nice job on defining it as people, pigs, and planet, and how we can improve our industry and define sustainable development goals. And if we look on the sustainability report that was published in 2021 by the National Pork Board, they have highlighted that in the past 6 decades, pork production has improved by using 75% less land, 25% less water, 7% less energy, and 8% fewer carbon emissions. So although this is good progress, as you can see, we still have a very long way to go. In addition to that, our markets and society as a whole are evolving. So if you go to the supermarket, you are going to see so many certificates and labels that indicates that animals were treated under certain welfare conditions and raised under specific welfare conditions, and also about the treatments and the production system in general. And there are certain supermarket chains that require specific welfare protocols in the farms in which they are buying their products from. So there are, in this context, some challenges or maybe opportunities for us to work with. So first, as we increase the proportion of group-housed animals, we need to take into consideration the fact that there might be increased agonistic interactions, tail biting, fighting, and so on. Also, there are, in several parts of the world, there are already restrictions on some physical alterations, such as tail docking. So that means we need to continue the process for domestication for animals that are more adapted to the current and modern production systems. Also, there has been a push for reducing or eliminating the use of antibiotics. We have also been suffering from antimicrobial resistance. So that means we need to have animals that are more disease resilient, that can cope better with this challenge. Also, for a very long time, genetic selection was mainly focused on a reduced number of production traits. that had antagonistic interactions with other robustness and resilience traits. And of course, the industry has realized it, and it is adding other robustness and resilience traits to their breeding goals to improve it. But that means we need to continue refining our breeding goals. Also, climate change is a big issue, so we need to breed animals that are more climatically resilient. So in other words, we need to use genetics not as the only solution, but as a complementary solution to also making improvements in the environmental conditions where the animals are being raised. But before we go further, I think it is important to define what I'm considering as resilience and robustness. We have already seen one definition, and there are multiple ones in the literature. So I define resilience as the ability of an animal to be minimally affected by an environmental disturbance or to quickly recover after they have been affected. So we can see here variability in feed intake. So there was an environmental disturbance, feed intake reduced, and then how fast the animal is able to recover from that will indicate how resilient that animal is. When we talk about robustness, that is basically the ability of an animal to maintain its production level in face of environmental challenge. So the ability of the animal to remain productive even when they are being challenged by disease and many other issues. And we cannot forget that the phenotype, what we measure, it is a combination of the genetics of the animal and also the environment. So here are just some examples: diet composition, temperature, pen density, and infectious diseases, and so on. And also there is an interaction between genotype and environment. So we all need to work together because the phenotype, it is a combination of both and not only genetics or only environmental management. So when we talk about genotype by environment interaction, what we are referring to is, let's say that we have here on the x-axis, we have our environmental gradient, which might be temperature, the health status of the farm, the diet composition, the pen density, and so on. And we have on the y-axis our phenotypic value. And we can see that certain, and each color represents one genotype. Imagine as a sire that will have offspring in different environments. We are basically saying that there are certain genotypes that under certain conditions perform better than others. In other words, there could be a re-ranking on how the individuals perform across environment. And you might be wondering, why is this an issue? Why do we need to take this into account? So we know that genetic improvement is usually done at the nucleus form, where animals are usually kept under high health conditions. There is usually very good environmental control. There is a high turnover rate. In other words, animals might not be kept until late age, and so on. However, animals are being selected to perform under commercial conditions, where there is much lower health conditions, there is less efficient environmental control, and also less than ideal management practices. And also, sows are expected to produce for a much longer period. So what do we need to make improvements in this area? So first, I think it is very important that we have data from both purebred and crossbred animals raised under commercial conditions, and this data needs to be transmitted to the nucleus herds so that it can be used for making selection decisions for performing under commercial conditions. We also need a better definition of the target production environments and a great diversity in the selection indexes. So we need to define where our animals are going to be expected to perform so we can adapt our breeding goals and also have maybe more diversity on the selection indexes that are available for picking breeding candidates. We need a better characterization of environmental conditions. So as I said, the phenotype depends on the genotype and on the environment. So we need to measure well what are the environmental conditions where the animals are going to be raised. And we need novel resilience and robustness traits that can be derived based on existing data sets and also using sensors and other technologies for deriving those novel traits that can be incorporated in breeding programs for improving resilience and robustness in the farms. So I will now go through some examples of deriving traits and what can be done. Some are work that we have done at Purdue, and others are work from the literature. And I will start with climatic resilience. And why is climatic resilience so important? So this is a report that just came out this year that shows around the globe where are regions in which there has been a greater increase in average temperatures. And we can see that in North America, Europe, and China, which are major pork producers, there has been an increase in average temperature much higher than the global average. And also, if we look at this plot here on the left, the last 8 years were the hottest on record. So that means this is and will become an increasing issue. When we look at the economics of that, there is losses of over $50 billion per year in agriculture around the world. And when we look in the US swine industry alone, close to $450 million in losses per year. If we look on an individual basis, that corresponds to $82 per sow only due to reproductive losses. So this is a major issue. So we have been working on, first, how can we use data that is routinely recorded in swine farms and data from public weather stations for deriving heat tolerance. So we worked with a breeding company that had farms spread across the whole US and also in Mexico. And we had different traits, reproductive traits, growth, and body composition. And then we gathered data from public weather stations close to the farms that we had the data. We observed that there is clear re-ranking for several traits. In other words, the animals that are the best for certain environmental conditions are not the best in other environmental conditions. And this needs to be considered for both selection and also when making management decisions, for example, where the animals are going to be raised. When we look at our ability to make predictions of heat tolerance based on genomic information and routinely recorded data, we see that we can obtain moderate genomic predictions. So that means we can already develop breeding values for heat tolerance based on existing data. And however, the point is that usually heat tolerance defined in this way tend to have a moderate and unfavorable correlation with production traits. So that means we can still make progress for both group of traits. However, we need to try to find better ways for increasing heat tolerance without compromising performance. Because as I mentioned at the beginning, sustainability needs to be economic, social, and environmental. So it has to be all the components. So in 2021, we had a trial in North Carolina where we measured close to 1,700 sows for more than 15 different indicators of heat stress response, including skin temperature in different locations of the body of the animals. We also used a vaginal monitor that's quite simple to make and cheap, so that we can measure vaginal temperature, let's say every 5 minutes, every 10 minutes, with like higher frequency. So automatically record vaginal temperature, also respiration rate, body condition score, hair density score, panting, hair cortisol. We develop an ethogram, ear pictures, and so on. So we collect different indicators to try to find biological indicators that might be less dependent on production. And in this paper, we have already published all the data collection protocols, so how all these traits were measured. And in addition to these measurements, we also had data, like in homologers, installed the same height of the sows within the barns. So we had to capture that microenvironment. And we also had data from public weather stations. And we wanted to compare how correlated the two sources of climatic variables were. And we had two building types, one enclosed room and one naturally ventilated. What we observed is that for the naturally ventilated, the temperature was, for both building types, the temperature was highly correlated, the one collected within barn or in the public weather stations. However, when we look at the humidity, for the enclosed barns, there was only a correlation of 0.48. This tells us that there is a great need for a better environmental characterization for breeding for improved heat tolerance in commercial conditions. When we look at the heritability of all these traits that were evaluated, we see that they are all heritable, and there are some, especially vaginal temperature, which is much more heritable compared to skin temperature. And this is in part because of the reduced environmental variability that we have, because we have a large number of records per sow and throughout the whole day instead of only specific time points. When we look at the variability in vaginal temperature throughout the day or across environmental gradient, in this case we were using dew point, we see that vaginal temperature is heritable throughout the environmental gradient and also throughout the day. However, there is variability. In other words, there are specific times of the day in which there is greater environmental influence. When we look at the genetic correlations between skin temperature and in different locations, we see that the genetic correlation is quite high, indicating that we can measure in any location and we are going to capture the genetic potential of the animals. When we look at the genetic correlation among vaginal temperature on different states, we also see that they are highly correlated. However, when we look at the genetic correlation between vaginal and the skin temperature, we only see moderate correlations, indicating that vaginal temperature is a better indicator of body temperature than skin temperature, because there is greater environmental influence in the skin. When we look at the genetic correlation among all those other traits, we see that in some cases there are only moderate correlations. And I will not go through all the details because we don't have time, but I just want to highlight that heat tolerance is a very complex breeding goal. So in other words, we can't have a single trait capturing the genetic merit of heat tolerance. We most likely need to develop a sub-index to capture variability for that. And out of those animals that we had measured in North Carolina, we then calculate their genomic breeding values, and we can see that there is a clear difference in the breeding values for the heat sensitive and heat tolerant. And we wanted to go one step further and do a biological validation to understand what was changing on those groups of animals. So my colleague, Dr. Jay Johnson and Mary Kate, his PhD student, did a biological validation by gathering two groups of divergent cells and measuring, using like an indirect calorimeter to measure the metabolic heat produced and also comprehensive phenotyping of those cells. And what we observed is that there is difference in heat and total heat production. There is difference on respiration rate, on skin temperature. And those cells, they became more, let's say, they were able to cope with the heat tolerant by increasing their efficiency in which they lose the heat, instead of decreasing their heat production, which is more related with production traits or production outcomes. And we also use the longitudinal data from vaginal monitors for deriving resilience indicators. So you can see that the vaginal temperature will range throughout the day, and we derive, so basically we look at different statistical metrics that capture the variability in body temperature throughout the day. And when we look at the heritability of the different indicators that we came up with, such as maximum vaginal temperature, the duration of that period in which the vaginal temperature was above the thermoneutral zone, we see that those traits are heritable and can be selected for. A second component is on feed-related traits. And this is a work that my colleague, Dr. Alan Schinkel, has done at Purdue. So for many years, they basically had piglets after weaning that received a soybean diet, and then they were sensitized afterwards for soybean protein, and their allergy or their allergic response to that was quantified. And they basically selected for multiple generations to either have a lower or a higher allergic response, and we can see that the two lines differed among themselves. When we look at the heritability estimates for soybean allergic response, it was around 0.20. And when we look at the genetic correlation with other traits such as birth weight, we saw that there was a negative genetic correlation, but it was weak. And when we look at the genetic correlation between soybean and peanut response, it was quite high, indicating that there is cross-reactivity. So this tells us that we can breed animals that are going to have lower allergic response to protein. So in other words, we can also work with this genotype by feed interaction that we might see in our farms and reduce the impact of those allergies, especially after weaning. Another area that is quite recent, and I think it will have major impacts in our industry, is actually deriving resilience indicators based on variability in body weight, feed intake, and feeding behavior. What you are seeing on this slide here, on each one, on the top row, it is a single animal, and on the bottom is also a single animal. And then we have different indicators, such as weight, feed duration, feed intake, and so on. You can see that on the top, there is lower variability from the expected, while in the bottom, there is a much higher variability, indicating that the animal in the bottom is a less resilient animal, is more affected by environmental disturbance. And when we look at the heritability of these traits that were derived either based on variability in body weight, variability in feed intake, or variability in feeding behavior, they are all heritable with heritabilities up to 28%. And also when we look at the genetic correlation between the deviations or the traits that were derived based on variability in body weight or variability in feed intake, they are highly correlated. So that means there is, if you are measuring one or the other variable, you might still be able to breed for that overall resilience using these data sets because they are highly correlated. And also there was a favorable genetic correlation with feed conversion ratio, which is a very important efficiency trait. So I think this is a very promising area for breeding programs. There are also many other alternatives. So one that I will not cover here, and Dr. Jack Deckers from Iowa State and also Pig Jane Canada have done very impressive research on the area of natural and experimental disease challenge, in which animals are measured under very challenging health conditions and evaluating the genetic background of how the animals respond to those health challenges, and so that this can be used in breeding programs. And now, with the more recent availability of genomic selection, this enables us or facilitates how we can connect data from commercial farms with nucleus, which before was much harder for us to make that connection, right? So now genomics will enable us to better use the data that is collected at the farm level. And of course, many of you guys, veterinarians, can help a lot with collecting this data and confirming the infections at the farm level so that this data can be provided to breeding companies to be used in selection indexes. Another very important area is the use of sensors and many other technologies for collecting additional indicators of robustness and resilience. And one of them is camera. And there are multiple examples already in breeding companies for detecting, let's say, locomotion and lameness, aggression behavior, tail biting, feeding and drinking behavior, and many other traits. This is a quite recent research area that I think it is very promising. And here are just some examples on how researchers have used cameras for detecting agonistic interactions. Here is another one using cameras for detecting body temperature of individuals that were infected with specific diseases, or also to detect laying position of the animals in the barn. So there is a lot of applications of sensors and other technologies for generating more data. So as final considerations, and I would say that resilience and robustness, they are multidimensional concepts, and therefore we won't find one robustness trait. We need multiple indicators of robustness and resilience to include in our breeding programs. Also, we need a lot of phenotype, and that are measured throughout the lives of the animals instead of a single time point. And most of these indicators that have already been evaluated, they are heritable with good genomic predictions, so that means we can add them to our breeding programs. I think breeding companies, they have done a quite good job in refining their selection indexes, and I think this is an ongoing process. So we are seeing progress, but I agree that we still have a long way to go. And we need more comprehensive environmental characterization. So it's not only measuring the phenotype and the genotype. We need to better characterize the environment where animals are being raised. We need to integrate data from commercial and nucleus farm conditions in genomic evaluations. And there are some breeding companies already doing that. And I think we should be using genotype by environment interaction data for making management and also selection decisions. And with that, I would like to thank again for the invitation, and I'll take any questions if we have time. Thank you.
Yes, we have time.
Thank you very much. The elephant in the room is the strong genetic correlation between the level of production and sensitivity to the environment. And that links very nicely to the previous presenter. He says, I have seen the levels of production go up, but sensitivity of these animals is going up too. So we have more and more problems. And then you have a long list of things which we could do about that environmental sensitivity, but that will go at the cost of the level, isn't it? What do you think we need to do?
That's a very good question, and I think it all depends on the economics and how we value, for example, let's say, heat tolerance, how animals are, or how do, let's say, consumers perceive if animals are, let's say, heat stressed. If you have, let's say, you have the impact from the consumers, we are going to have what is the impact of those on production levels, and then we need to balance it out. And also, I think it all depends, are we able to control the environment, or do we need animals that need to be resilient and robust in challenging conditions? And that's why I meant that we need to have a greater diversity on selection indexes, because if we have, let's say, very intensive selection conditions, it might be okay if we give greater emphasis on productivity. But if we have or if we expect animals to perform in more challenging conditions, which is usually the case in commercial farms, then I think we need to prioritize those traits, even if it might lead to reduced or slightly reduction in production. Those other traits might result in greater economic return to the producer than only focusing on production. So, and there are ways that
all
we...
the presentations I've seen so far about robustness and mortality, production was never ever mentioned almost. So I think that the feeling at this conference is we need to adapt the animals to the environment, and better even, one of your first slides you said 85% of the animals is raised under suboptimal conditions. Only 1% is in a real nice. We need to improve that environment, and we need to do something at the sensitivity, even if it's at the cost of production, in my opinion.
Yeah, I would agree with that, yes. I think we need to work like on trying to improve the environment. And we need also, as we are selecting, let's say, that small proportion of animals that are maintained under high conditions, we need to make sure that we are using the information from, let's say, their descendants to make decisions at the nucleus form. And it might actually be focusing on other, let's say, robustness traits, and maybe not as much on production. So I think we might need to consider both, yeah.
Well then, thanks very much,
Thank you.
Dr. Ruiz.